Here we have another spring problem. If 6 joules of work is needed to stretch a spring from 10 centimeters to 12 centimeters, and another 10 joules is needed to stretch it from 12 centimeters to 14 centimeters, what's the natural length of the spring? This is different from the previous problem because we don't know the natural length of the spring. So for this 10 centimeter starting point, we don't actually know how far that is beyond the spring's natural length. But let's just mark the 10 centimeters there. And then it's going to be stretched to 12 centimeters. And then we're going to stretch it again to 14 centimeters. We've got that 6 joules of work were required for the first stretching, and 10 joules of work was required for the second stretching. We're going to use Hooke's law, which is f of x is equal to kx. But in this case, we don't actually know what x is. Here's what we do know. The starting point for this whole process, 10 centimeters, is some distance beyond the spring's natural length. Actually, that's an assumption, but it's an assumption that makes sense. Anyway, if this is a length of L and this is a length of 10 centimeters, then this is a length of 10 minus L centimeters. And I notice I marked this as meters up here, and it should be centimeters. We then know that the distance from the natural length to the 12 centimeter mark is 12 minus L centimeters. And the distance from the natural length to the 14 centimeter mark is going to be 14 minus L centimeters. Okay. Where f of x equals kx is showing up is in our integral for work. We know that work is an integral from a to b of, in this case, kx dx. We have all our limits of integration. We have the form of our integral. Let's write this down. So for the first bit of work, 6 joules are required. The integral goes from 10 minus L to 12 minus L. Those are the limits of integration. And the integrand is kx. Don't forget dx, right? Force times distance. Second bit of work, stretching from 12 to 14 centimeters, 10 joules are required. Lower limit of integration is 12 minus L. Upper limit of integration is 14 minus L, and then the integrand itself is kx dx, and I have messed this up, but it's an easy fix. Folks, all this is in centimeters, so these need to all be in meters. Therefore, I need to write this as 0.14 minus L, and these should both be 0.12 minus L and 0.1 minus L. Or 0.10 minus L, I don't care. Anyway, they should be in meters. My bad there. Now, these are possibly the weirdest equations we've ever seen because we have kx dx, it's an integral, but the thing that we're after, the natural length of the spring, L, is in the limits of integration. Totally weird. Let's back up, though. How did we know that we needed to set up an integral and not start with f of x equals kx? The answer is we were told how much work was needed to stretch a spring. It's not like the previous problem in which we were told the force that was required to hold a spring. Okay? So we have to pay close attention to the information that we were given. Integrating these is pretty straightforward. We're going to use the power rule. K over 2x squared is equal to, 6 is equal to k over 2x squared. And that gets evaluated from 0.1 minus L to 0.12 minus L. Likewise, 10 is equal to k over 2x squared, evaluated from 0.12 minus L to 0.14 minus L. And so for the first one, 6 is equal to k over 2 times 0.12 minus L quantity squared minus 0.1 minus L quantity squared. Before we go any further, I see that in the brackets here, I have two terms. It's a difference of squares, right? This is like a squared minus b squared. That factors into a plus b times a minus b. All right, so let's see what that becomes. A plus B. So that's 0.12 minus L plus 0.1 minus L times A minus B. So that's 0.12 minus L minus the quantity of 0.1 minus L. These simplify, and we get 0.22 minus 2L in the first set of parentheses, and in the second set, the L actually subtracts out, and we have 0.02. So that times k over 2 is equal to 6. And you can verify that for the other integral, we end up with 10 is equal to k over 2 times the quantity 0.26 minus 2L times 0.02. This is our system. Oh, by the way, we had in each of these equations k, x, and L, and that seemed like a whole lot, and it was, but when we integrated with respect to x and then evaluated at the limits, we no longer have an x in the equation. So what we ended up with was two equations that each have two variables. This is a system of equations. We have k and we have L. We're after L. And turns out, if I have equations that have one term on each side, and that's what we have, right? 6 is equal to a product. That's one term. Then I can like divide one equation by a number. It's kind of, by another. It's kind of cool. And in this case, if I do that, then on the left-hand side, I get 5 over 3. On the right-hand side, k over 2 divides out, 0.02 divides out, and I end up with 0.26 minus 2L over 0.22 minus 2L. You'll notice the calculus was done long ago. We're just seeing how to deal with this algebraically. Well, this is now a proportion, so I can cross multiply. And I end up with 1.1 minus 10L is equal to 0.78 minus 6L. That's going to give me that 0.32 is equal to 4L, which means that L is equal to 0.8. Let's go back to our problem here. And what we had done is we had these limits in meters, right? So this is 0.08 meters. So we now can say that the natural length of the spring is 8 centimeters, and that makes sense because at the outset we kind of expected that length to be shorter than 10 centimeters.